form of equation. It's just a general equation.
Oh.
You need to have a test point.
Here we go. Okay, so yesterday we did just a review of parametric equations from back when you were in pre-cal, maybe. Now we're going to do parametric equations in calculus. And by the way, yes, parametrics are a real thing. You're going to do it. Got an email from a former student, his brother, Harry, and it was like, because I kept telling him, you're going to use this if you go into chemical engineering. I know for a fact because I used it. Well, he went, yeah, you need parametrics for tank problems. He says, we've done Riemann sum, Simpson's rule, trapezoid rule, all those integration techniques. He pretty much he's saying, I'm using it all still. And so I laughed, said, told you so. Like, when are we ever going to use this? In college, if you go into engineering. That's what I know. Anything else, I don't know. But I know for a fact in engineering you will. So here we go. Parametrics. The thing here is for parametrics, these are smooth curves. Well, I can't spell. But that's why I teach math, because I can't spell. Smooth curves. What I really can't do is walk, and write at the same time. Which means what? It's differentiable. The parametric means you have y in terms of time and you have x in terms of time. The parametric means there's another parameter. It's t. So actually what I should have written is y is equal to some function in terms of time, and well, let's just call that g of t, and x of t is f of time. So you have your x and y in terms of functions in terms of time. So we can describe how the y is changing with time, how the x is changing with time. Now, if it's differentiable, does that mean all the derivative things you can do to these? Yeah, and that is kind of the whole point. We have to get back to a concept. Remember that dy dx, where did it come from? It came from a change in y over a change in x, right? So if they're both changing with time, just in terms of algebra, if we have delta y changing with time over delta x changing with time, can we simplify that to delta y over delta x? So you're given an equation that you're given two equations in terms of their functions of time. I can take their derivatives, and that tells me how the y is changing with time and the x is changing with time. If I divide them, it gives me dy dx. It really does work. Okay, so that's the algebra. Then there's the calculus. Bless you. Allergic to parametric in calculus, huh? So if I want dy dx, because is that going to be a real thing? Even though they give me the equations in terms of time, are they going to want the slope at a particular time? Yeah. Are you going to have to find dy dx? And dy dx is dy dt, so the derivative of that y equation in terms of y divided by dx dt. Really, really. What can't be equal to 0? Dx dt can't be equal to 0 because then it's undefined. That wasn't bad. So the first derivative makes sense. And then there's the second derivative. You just need to memorize it. It's messy. It really is. And I just memorize it. It's so much easier if you'll just memorize it. As I was going through my homework last night and they were changing variables on me and I was, taking derivatives with respect to x of something that had time in it, just like this, and it's messy. Okay, so that means I'm taking the derivative with respect to time, with respect to x of dy dx, which was dy dt over dx dt. You see why this is going to be a problem? Do you see why it's a problem? It's a quotient. You're taking the derivative with respect to x of a quotient that is not always with respect to x. It's with respect to time. It's implicit. Okay, will you just accept the formula then? Because I really don't want to, my head doesn't hurt. My head hurts too much to show you how to do this properly. So we're just going to accept the fact that this is going to end up being the derivative with respect to time of dy dx over dx dt. So you know how you got an equation for dy dx in terms of dy dt over dx dt, right? You're going to take that derivative, which is in terms of time, and then you're going to divide it by dx dt. And that will give you the second derivative with respect to x. And you're just going to have to memorize it for now. If my head isn't hurting, I'll figure out how to show it. It's kind of messy. And conceptually, it's a little, it's interesting. Okay, and I can lose myself, so I can really lose y'all. Then there's arc length. Remember arc length? But it's a little different now. Remember how we just did 1D? Now we got to do 2Ds. This one's actually easier. Okay, we use S for arc length often. It is going to be the integral from A to B of the square root of, do we have the derivatives in terms of time for each one? Because this is just, remember, this is just, we're integrating the distance formula. So it is literally going to be just dx dt squared plus dy dt squared dt. That's actually easier to remember. It's just you're integrating the distance. And in calculus, the distance this time is it's dx dt and dy dt. Isn't that amazing? You should memorize all of these. So I'm going to put a red box around them. You should memorize the calculus. Some of them are easy, some are harder. Okay, so let's do some examples. Is it hot in here, or am I having my own personal summer? Nobody's answering. It is hot? Okay. I'm not losing my mind. You're saying possibly. That's a good answer. But it is warm in here, so it's not just me. Okay, would we rewrite that? We would rewrite that to 2 equal to 2t to the 1/2 power, right? Okay, they give you this, and they want you to find dy dx. That's part A. We'll call that part A. In part B, I want you to find the second derivative, because I'm just that wicked, because they will too. So I have to be wicked also. So for part A, if I want dy dx, do I need dy dt? So for the y, what's the derivative of y with respect to time? 6t minus 2, right? What's dx dt? It's going to be 2 times a half, which is just, and then it's t to the what power? Negative 1/2. So if I want dy dx, it is equal to 6t minus 2 over t to the negative, sorry, yeah, it's negative 1/2. Which, if it's negative power, what do? I'm going to flip it up, right? So it's going to be square root of t times 6t minus 2. That wasn't bad, was it? Okay, that one was easy. Now, we should rewrite this. Okay, for purposes of an answer, that's okay. Do you want to take the derivative that way? No? No? You should distribute. So another way to write this, if we're distributing the t to the 1/2 power, is this going to be 6t to the 3/2 power minus 2t to the 1/2 power? Is that the way we want to show it if we're about to take the second derivative? Is what we want to show. So if I want part B, and I'm finding the second derivative of y with respect to x, that means it is the derivative with respect to time of my dy dx, which was 6t to the 3/2 power minus 2t to the 1/2 power. You see what I was talking about now? And is that all divided by dx dt? And what was dx dt? T to the negative 1/2 power. So we take this derivative with respect to time. What is the derivative of 6t to the 3/2 power? 9t to the 1/2 power minus, what is the derivative of 2t to the 1/2 power? T to the negative 1/2 power. All over t to the negative 1/2 power. And if you remember when you're simplifying exponents, which I've been doing in pre-cal today, so it's, if we break, should we break this into fractions? Have y'all learned that yet? Is it going to keep happening till y'all get it? Actually, it why would it be plus? I'm taking a derivative, so I've got a positive half times 2. This was a negative. I'm not dividing. It's derivatives, not integration. Yeah, we have to keep that straight. Okay, break this into 2 fractions. Is this going to simplify to 9 times, well, I have t to the 1/2 minus a negative 1/2 means it's t. Yes? Everybody got it? And then this one, is that just 1? So it's minus 1. So that is equal to the second derivative. And that wasn't a bad result, was it? You just had to get there. They're actually kind of fun when you get the hang of them. They're fun compared to what I have to do. Okay, everything we can do with derivatives, we can do with parametric. They're not going to do related rates, but they are going to do derivatives, second derivatives, tangent lines, yeah, slopes, horizontal, vertical lines, yep. So for our second example, I'll go to another page, maybe. Example 2. Write the equation of the tangent line. Oops, that was messy. At t equals to 3 pi over 4, do you suspect trig? You should. Given the following, x of t is equal to 4 cosine of t, and y of t is equal to 3 sine of t. Okay, for starters, do we have the ability to find the point of tangency just looking at this? I want the x and y coordinates.
Plug in the time.
Thank you. Y'all are going to make this harder than it is. Do you see that you have the time and the equation for x and the equation for y? If you plug in the time, do you find the point? So we got to find the point of tangency first, right? So we're going to find the point. The point is going to be x of 3 pi over 4 is equal to 4 cosine of 3 pi over 4. And what quadrant is that in? Second. And if it's in the second one and it's a pi over 4, what's the cosine, which is the x coordinate? Negative square root of 2 over 2. So is this going to equal 4 times negative square root of 2 over 2, which means it's negative 2 square root of 2. Yes? All right. For the y coordinate, it's y of 3 pi over 4. That's going to be easy. Equals 3 sine of 3 pi over 4. What is the coordinate for the y in the second quadrant? Huh?
Positive.
It's the square root of 2 over 2, right? So it's going to be 3 square root of 2 over 2. I'm done. My point is going to be negative 2 square root of 2, 3 square root of 2 over 2. That's my point. What else do we need to write the equation of a tangent line? The derivative, because the derivative is, it's a line, slope. It's the slope. I need slope, right? Slope in calculus. I need the slope. Does that mean I need dy dx? OMG. Does that mean I need dy dt over dx dt? I'm showing you how I actually do these. I don't break them up. I don't even write that. I would just immediately go, for the y, can you take its derivative? What's the derivative of 3 sine of t? 3, what's the derivative of sine? Cosine of t. All over 4, and then what's the derivative of cosine? So it's negative sine of t. Yes? So that's just my general equation. Can I find the slope? And I need y'all to practice the notation correctly. If I actually want slope, so that's actually just a derivative. If I want slope, do I have to evaluate that slope at that time? Slope means that it's going to be dy dx evaluated at t equals 3 pi over 4. Yes? So is that going to equal 3 cosine of 3 pi over 4? We've already found that, haven't we? You're going to keep using stuff. We found this. We found 3 pi over 4 for cosine. We just have to multiply by 3 this time instead of 4. Do you understand what I'm saying? This one is going to be negative 4 sine of 3 pi over 4, which means I have 3 square root, so it's negative 2 over 2, right? And then for this one, I have negative 4 times a square root of 2 over 2. Yeah? Weigh what? You got it? Okay. So, do you see that they both have a square root of 2 over 2? Don't go ahead and multiply it out. Can I just get rid of it and just say it's 3/4? I didn't forget no stinking 3. You could, but are you better at cotangent than sine and cosine? I know it is. I know. Yeah, I didn't realize that. I said pi over 4. It's easy. That's fine. You can do cotangent. That's so good. That's good. But is it 3/4? Can we write the equation? We aren't done yet. We have to write the equation of the tangent line now. What do? Y what? Minus what? 3 square root of 2 over 2 equal, what was my slope? 3/4 x plus 2 square root of 2. I won't press the easy button. I think it's easy. I like them. They're fun. Y'all should worry. Okay, guess what? There's more. What if I want to find all horizontal and vertical points of tangency? I'm doing this because these are the questions on your assignment, right? I was getting carried away. I was writing find all in one word. Find all horizontal and vertical points of tangency. What does that mean if it's horizontal? What kind of slope does it have? What about vertical? Undefined, right? So you have division by 0. Well, let's find the equation for the slope, and then I'll show you how easy this is, right? So we want dy dx. Oh wait, I didn't give it to you yet. Okay, x of t is equal to t squared plus t, and y of t is equal to t squared minus 3t plus 5. So dy dx, what is the derivative of the y with respect to time? 2t minus 3. What's the derivative of x with respect to time? 2t minus 1, right? Or plus 1, plus 1. Okay, if I want horizontal tangent lines, it's when 2t minus 3 equals 0. If I want vertical tangent lines, it's when 2t plus 1 equals 0. Does that make it easy? It does. So for this, I need my time to equal 3/2. For this one, I need my time to equal -1/2. Agreed? That's the easy part. Now there's the, we actually have to go find the points. I'm going to go to the next page if that's okay with you. I'm going to copy this. What we got to. Copy this. Go to the next page. Paste it. I know this is actually, now that I'm getting the hang of it, this is so much more fun. It actually makes it more better. It makes it easier. Until I mess something up. That is. Okay. So for this one, if I want horizontal, I need time is 3/2. So that means my x of 3/2, it equals to 3/2 squared plus 3/2, which is 9/4 plus, well, I can do 3/2 into 4, so that becomes 6/4. Yes? Which is 15/4. And my y of 3/2 is equal to 3/2 squared minus 3 times 3/2, and then plus 5, which I'm going to change 5 to 10/2. So this is going to be 9 minus 9. Oh, wait, those don't go away. Yeah? No? Oh, it's 9/4.
Yeah, it becomes.
I got carried away. I was hoping it would get, oh, it still gets better. That's still going to be fine. Plus 10/2. Well, that means I got -9/4, right? -9/4. And let's put this into fourths, so that becomes plus 20/4. What's 20 minus 9? So it's 11/4. So my coordinate, my point of tangency where it's horizontal, is a 15/4, 11/4. Can't even write. Is that my point for horizontal tangent lines? Yes? What about vertical? For vertical, we're going to plug in -1/2. So my x at -1/2 is equal to -1/2 squared minus 1/2. And I'm just going to do the y of -1/2 right parallel with it is equal to,
Plus. Oh, well, no.
yeah, right?
Yeah.
So -1/2, you'll need to watch me because my head hurts and I'm not mathing so well today. Minus 3 times a negative, which means it's plus 3/2, and then plus 5. So if I keep going with the x's, this is going to be 1/4 minus 1/2 is a -1/4, right? This one, y at -1/2, is going to be a 1/4 plus 3/2, which is 6/4 plus 20/4, right? Is that 27/4? So my point for vertical tangent points of tangent line is -1/4. I said that all backwards. If I want to find where it has a vertical tangent line, it is at the point -1/4, 27/4. That has a vertical tangent line. Okay, last kind of problem. on the last kind of problem. This is for arc length. So example 4 is just set up an integral to find the arc length. Set up integral to find the arc length of the curve x of t is equal to t squared plus 1, and y of t is equal to 4t cubed plus 1 from 0 to 1, whatever seconds or whatever units it is, days, minutes, nanoseconds, if it's a particle motion. Okay, what do you need to find arc length? Derivatives. Is that just, it's just Pythagorean theorem with derivatives. So what's dx dt? 2t. What's dy dt? 12t squared. What you're going to find is the calculus steps are not hard on any of these. So if I want arc length is equal to the integral from 0 to 1 square root of my x, which is 2t squared, and then my y derivative, which is 12t squared dt. And that's it, I'm done. And the problem with the arc length is they tend to produce things that you don't know how to integrate. That's why they're on the calculator section. They really are. They're on the calculator section, or they're on the calculator section of the free response, and you get a point for setting up the integral curve correctly, and you get a point for knowing how to use your calculator.
Knowing how to use the calculator.
You're going to have to use the calculator. Okay, stop.